In this video, we're going to construct a harmonic series for a glottal source tone, the sound produced by the vibrating vocal folds. We're going to calculate the resonant frequencies or formants for a vocal tract tube and draw the filter function for that vocal tract. And then we're going to draw the output spectrum for the vowel sound that's produced when we pass this glottal source tone through the vocal tract filter. So first, let's draw a source spectrum for a vowel that has a fundamental frequency of 300 hertz. The vocal folds are vibrating back and forth at 300 times per second. Those are pretty small vocal folds, so maybe they belong to a child. The amplitude of the fundamental frequency component is 60 dB SPL. And this is a pretty typical voice, so the amplitude of the harmonics falls off or rolls off at a rate of about 12 decibels per octave. And remember that an octave means a doubling in frequency. So what I like to do is draw myself a table. And I'm going to start by putting in the fundamental frequency, which is 300 hertz, and its amplitude, which was given, is 60 dB SPL. Now we can calculate the frequencies of each harmonic very easily. So the second frequency is going to be 2 times the fundamental, or 600 hertz. And we'll have 3 times the fundamental for the next one, 900 hertz, 1200 hertz, 1500 hertz, 1800 hertz, 2100 hertz, and so on. And we can keep going all the way up to 3000 hertz on this particular diagram. The amplitude is a little bit trickier. We can only calculate the exact amplitude for the frequencies that, or the harmonic components that fall at octave distances from one another. So in other words, we can calculate the amplitude for the harmonic that's 2 times the fundamental, 4 times the fundamental, 8 times the fundamental, 16 times the fundamental, and so on. And the other values we'll have to estimate. So here I've calculated the amplitude for the second harmonic. I take the original amplitude, 60 dB. We know that it falls off at 12 dB per octave, so I subtract 12 decibels, and I get 48 dB for that second harmonic. I don't get an octave distance until I come up here to 4 times the fundamental. So the distance between 600 hertz and 900 hertz is not double 600 hertz. That doesn't occur until 1200 hertz. So I take the amplitude for the second harmonic, 48 dB. I subtract 12 decibels, and I get 36 decibels. And then I have to skip all the way up here for the next doubling of frequency to the 8th harmonic. So I take 36, which was the amplitude for the 4th harmonic, minus 12 equals 24 dB. And I can plot all of those values over here on my source spectrum. So remember, we've got frequency along the x-axis and amplitude along the y-axis. And so here's my 300 hertz component. It falls at a frequency of 300 hertz. It has an amplitude of 60 decibels. And here at 600 hertz frequency, for my second harmonic, I have an amplitude of 48 dB. Here's my 4th harmonic, falling at 1200 hertz with an amplitude of about 36 dB. And here's my 8th harmonic at 2400 hertz with an amplitude of about 24 dB. Now I can estimate the other values. And what I often do when I'm using pencil and paper is just put a ruler down and just see, oh, I think I'll estimate that the amplitude for this 3rd harmonic falls at about 48 or 47 dB. And I just estimate the other ones too. You have to actually turn the ruler so that it's always falling between 2 harmonics where you know the exact amplitude. So that's our source spectrum. We know that the fundamental frequency is 300 hertz. And so we have multiples of 300 hertz. And then it was a little bit tricky to get the amplitude values. And now we have a nice normal spectral tilt. Okay, so let's draw ourselves an amplitude spectrum for a vocal tract filter. If that open closed tube is 0.15 meters long And let's say the speed of sound in air is 340 meters per second. So we want to calculate the first resonant frequency, F1, the first formant, formant number 2, and formant number 3. And remember that this open closed tube only produces odd harmonics because it's a quarter wavelength resonator. So the second formant or resonant frequency actually represents the third harmonic of that vocal tract tube. And F3, the third formant, is actually the fifth harmonic. That's going to fall out of our formula. So if we use this formula, the frequency of any particular mode of vibration, which is n, equals 2 times n minus 1, that always gives us an odd number, times c divided by 4 times the length of the tube. So we're just going to plug in some numbers here. For n, for the first mode of vibration, we'll put in 1. So 2 minus 1, 2 times 1 minus 1 is 1, times 340 divided by 4 times 0.15 meters equals 567 hertz. And once we get the first one, the other ones are pretty easy. We just multiply the first one by 3 to get the second formant. We get 1701 hertz. And we multiply the next one by the next odd number, 5, and we get 2835 hertz. Or if you want to work it out the long way too, just by plugging in 1, 2, and 3, you can do that as well. So now we know the formant peaks, the formant frequencies for each one of our modes of vibration, first 3 modes of vibration for our open closed tube. And those are the ones that are important for perception of vowel identity. Okay, I also gave you in the homework problem some amplitudes for each of those formant frequencies. And so for the first formant frequency, I'm giving you an amplitude of 0 dB SPL, and we can just plot a dot at 560 hertz at 0 dB. For the second formant frequency, you're given that amplitude. It's minus 10 dB SPL. That means we're going to take off 10 decibels of amplitude from any frequency that happens to fall at that location. I'm just going to plot a dot here, 1701 hertz, minus 10 dB. And then for my third point, it's going to be at minus 15. So there's 2835 hertz, and I'm plotting my little dot here at minus 15 dB SPL. And then I'm just going to sketch in the rest of the curve. So on the homework problems, everyone's going to have something that looks a little bit different, and that's okay. So now I have my vocal tract transfer function, and again, I've got an amplitude spectrum with frequency along the x-axis and amplitude on the y-axis, and this tells you how many decibels either to add or to subtract at each frequency for your glottal source spectrum. All right, so this is getting a little bit more complicated. So let's pass our source spectrum through our vocal tract transfer function and see what our output spectrum looks like. So here's my source spectrum here, right? And so remember that I had 300 hertz fundamental frequency with an amplitude of 60 dB. And then here's my next component, 600 hertz with an amplitude of about 48 dB and so on. So I'm going to take each one of these harmonic frequencies and pass it through this vocal tract transfer function. And again, I like to have a table to keep myself organized. So for my 300 hertz source component, which has a 60 dB amplitude, I'm going to look here at 300 hertz. I'm going to go up here, and it says take off 15 decibels. So I'm going to take the original amplitude of 60 minus 15 equals 45 dB. And I'm going to plot that right here. So you can see that, oops, sorry. I'm going to plot that right here. And you can see that even though I had an original amplitude of 60 hertz, this vocal tract filter removed about 15 dB worth of amplitude, and that's reflected right here. All right, let's go to our second one. So here's our 600 hertz second harmonic, and we're going to go over here and see what it says to take off. It says to take off 0 dB. So my original amplitude was 48. 48 minus 0 equals 48 decibels, and I'm going to plot that right here. And you can see that I just keep doing that all along the way. And I plot all these frequency components here. And you can see right here between 2000 or between maybe 1800 and 2600 hertz that we took off so much amplitude that these guys disappeared. And then I just see a little hint of this harmonic in the third formant region. So this reflects our first formant peak. This reflects our second formant peak. And this reflects our third formant peak. We had big troughs or valleys where lots of amplitude was removed around these frequencies here. So we don't see much evidence of them left. You can use E-System to sort of check your answers. So let's go over to look at that. Okay, so I'm going to put in a sawtooth waveform because that most closely approximates the sound produced by the vibrating vocal folds. And our fundamental frequency was 300 hertz. So I'm going to put that in there. And you can see we've got this nice sawtooth waveform here. And this is the input spectrum, and it looks a lot like ours, right? So here's our fundamental frequency, second harmonic, third harmonic. Now we weren't able to specify the amplitude of each of these frequencies, and so they're slightly different from ours. So for this one, it looks like it's at about 57 rather than 60 dB, but the harmonic spacing, the frequencies are right. And here's what it sounds like. That horrible buzzing sound that's produced by the sawtooth waveform. Now we have to create the vocal tract filter. So I'm going to click here. I'm going to make a vocal tract filter, right? And let's see, my frequencies, I'm not going to remember exactly, but they were about 560, about 1700 and something, and about, what was it? Let's see, so 560 times 3. Let me get out my calculator. 560 times 3. Oops. Times 5. Okay, about 2800 hertz. Again, not exact, but we're going to be coming close. And you can put the exact numbers that you calculated. I just forgot to write mine down. And so here you can see our vocal tract filter that we've got a peak here around 560 hertz, one around 1700 hertz, and one around 2800 hertz. That looks pretty much like ours. Again, we weren't able to specify the amplitudes of those peaks, so they're a little bit different from the ones I gave you. And here we can see the output spectrum. So we can see here's our 300 hertz component, and it basically got boosted a little bit. So it was told to add a couple of decibels of amplitude. Same thing with our 600 hertz component. If we follow what this says, it says add 20 dB to the original one. And so you can see that first formant frequency reflected here. And then we keep going. You see the evidence of the second formant frequency peak and a little bit of evidence of the third formant frequency peak. So let's see how the sound changed as we pass this tone produced by the vibrating vocal folds through a vocal tract filter for a particular length and see what it sounds like. So again, here's our original sound. And this should be a more vowel-like sound. Kind of makes a neutral vowel something close to schwa. All right, and so now you should have a good idea of how to get started on your homework.